Yeah, in this video we try to discuss about simple harmonic motion, and we find in the study of physics there are many systems which exhibit simple harmonic motion, and the different types of motions which we study are the one-dimensional motion, which is also known as straight line motion, and the Newton's equation for this type of motion is the acceleration is equal to the force by mass. Now the next type of motion is the 2D motion, and the fundamental 2D motion is a projectile motion. In this case, we find that the motion in one direction has a constant speed. Suppose if we take that to be dx by dt is constant, and in the other direction, the y, that is in the direction of the gravity, it is given by g, where g is the acceleration due to gravity. And we know that all two-dimensional motions can be studied as combination of two single-dimensional 2D, two one-dimensional motions. The other two-dimensional motion is the uniform circular motion. Uniform circular motion, where the object goes in a circle with a uniform speed. So in this case, we study that the path of the particle is given by x square plus y square is equal to a square, where this is the radius, or 2a is the diameter of the circle in which along which the object is moving. Now, if you observe this motion, if we try to study the circular motion as a combination of two one-dimensional motion, that is x and y motion, we can see, suppose if we take a particle at this point, it has got a projection on x-axis, it has got a projection on y-axis, and the projection on x-axis is given by, suppose if this is angle theta, then the projection is a cos theta and y is a sin theta, and this will give us x square plus y square is equal to a square cos square theta plus a square sin square theta, which will give cos square theta plus sin square theta is 1. So we will get x square plus y square is equal to a square. So we see that if we know the equation of motion for two one-dimensional motion, and we can combine that to get the two-dimensional motion of the object. And here we see the projection on the x-axis or the y-axis. As a particle at this point, the projection is 0. The x is a, the y is 0, and x is a. At this point, the projection of x is plus a, and the projection of x is minus here, and the projection of y is plus a here and minus a here. Here y is 0, here x is 0, here x is 0, and here y is 0. So this is how. So we see that the two single one-dimensional motion will give rise to 2D motion of the object, and this projection on x-axis changes from, it is going from, for suppose it is starting at this point at t is equal to 0, then the starting is plus a, then it becomes 0, then it becomes minus a, then again it becomes 0, then again it becomes plus a as it goes around the circle. So this is the starting and this is the ending. This is one cycle. So in one cycle, we can see that it is the projection is changing from plus a to minus a, and then it's going to plus a. And this type of motion, where again, if the motion continues along the circle, again this goes on repeating. So we can see it is as if the particle, it is similar to a particle going like this. So this is a, it starts from here, then it goes like this, then it goes like this. If you visualize the projection is going like this to the left and to the right. This is plus A and this is minus A. And this type of an oscillation is known as simple harmonic motion. Simple harmonic motion, and the displacement of the particle undergoing simple harmonic motion is given by A cos, let us say, theta. We'll try to understand what exactly the theta is. So the uniform circular motion is nothing but combination of two perpendicular simple harmonic motion. That is, along y it is A sin theta, along x it is A cos theta. So the combination of two one-dimensional motion gives rise to two one-dimensional simple harmonic motion gives rise to uniform circular motion. So now if we try to further study this, in general, suppose the particle starts its journey from here, and this is phi, and it has got an angular velocity of w, angular velocity, and we know that v, the linear velocity, is equal to rw. So this is angular velocity, or is the radius. Now in this case we are taking a, so v is equal to aw. A we take to be the radius of the circle in which it is moving. So if this is the position at t is equal to 0, then after time t, this angle is theta is equal to wt, because this is angular velocity time t theta. So the total angle is theta plus wt plus phi. So we will find this x is nothing but a cos wt plus phi. So this is in general the displacement in simple harmonic motion. And if phi is 0 at theta, that is at t is equal to 0, if it is starting here, then it becomes if t is equal to 0, if the amplitude is a, then phi is 0. That is, the particle starts moving from here, then we take x is equal to a cos wt, and phi is known as the phase. That is the starting point from where it starts moving. So this is in general equation for simple harmonic motion. And we know that the acceleration of the particle which is going in a circle is given by a is equal to v square by r, and in the direction minus r, that is towards the center. So if we try to take the x component and y component of the acceleration, at this point the acceleration is like this. So the component along this, suppose if this is theta, then the component ax is minus v square, or then I, that is, this is the x component and this is the y component. So ay is minus v square by r j, so this is cos theta and this is sin theta. This is theta. So this cos theta, and here it is sin theta because this side, this is sin theta. Now we know that in translating from Cartesian to circular coordinates, we know that x is equal to r cos theta and y is equal to r sin theta. By plugging in this, we find ax is equal to minus v square by r square x, then I, that is the minus I direction, and ay is nothing but minus v square by r square y. Now this is j, minus y direction. So here what we find is v square by r square is omega. Now we will restrict our discussion to only one component, only x. So ax is nothing but minus omega square x. This is the acceleration in the x direction, and we see that omega, omega is nothing but v by r. So if there is an acceleration which is proportional to x and directed opposite, then any motion which obeys this equation is called simple harmonic motion. And we see how the terminology of angular frequency comes in the discussion of simple harmonic motion. That is, it draws the terminology from this, that the simple harmonic motion is only the motion of a particle, the projection of motion of a particle which is undergoing uniform circular motion. So the two systems, simple systems which undergo simple harmonic motion are the spring, mass m connected to a spring. Here the equation is md square x by dt square. The force is always proportional to the displacement. So if you stretch, this is the equilibrium position, and if you stretch the spring by a displacement A, then there is a potential energy stored because a work is done when you pull the spring. Then because of this potential energy, the particle executes simple harmonic motion from plus A to minus A. It is similar to a particle which is in a bowl, and then if you just replace it, it starts oscillating to and fro. So this is an example of oscillation or a simple harmonic motion. And the other example is the case of a pendulum. We just raise the pendulum, then this will undergo simple harmonic motion. So in this case, the suppose this is the L is the length of the pendulum, and you have the force mg. There is a mass m. This is mg, and the tension in the spring balances with this component of the gravity, and the other component of the gravity gives rise to acceleration. Now we can show that the equation here is theta is equal to theta max and cos omega t. Also, we can also show x is equal to this. This is the amplitude. This is x. Maximum value of x is this, if you take this to be along the x-axis. So that means we can treat this both as a linear motion along this projection, like we have taken the circular motion projection. So this is a rotational motion, but we take the projection of this. That also will undergo the simple harmonic motion. This is x. If this is a maximum is a, then so we can either take this as an amplitude or this as an amplitude. So it is valid for both. So this is here the omega is nothing but omega is root g by L. So here in this case the omega is, in case of spring, omega is k by m root. This is spring, omega spring, and this omega pendulum is root g by L. So this this actually we can derive the equation using the rotational motion. Just show that how to derive this. You have, so the force here is mg sine theta. Now or we can take this as mg, then we can take the distance here as L sine theta. So the torque is mg L sine theta, and again as theta increases, it is opposite to the increase in theta, so we'll have minus is equal to I alpha, the moment of inertia, if this is mass m and this is length of the pendulum is L, then moment of inertia is L square, and the angular acceleration is d square dt square. So we are basically writing using the equation tau is equal to I alpha. So this will give for small theta, this becomes theta, then we will find d square theta by dt square is equal to minus g by L theta. This equation we will get. So by plugging in, so this equation for theta, so this will give us the equation theta is equal to theta max cos omega t, and here omega, as we see, is omega square is g by L. Now we also see when for small theta, this and arc are same, and we know the arc length is nothing but nothing but L theta. So which is same as x is equal to L theta. So we plug in theta is equal to x by L. Then we can plug into this theta is equal to x by L. Then we'll get x is equal to x max cos omega t. Or we can plug in straight away here and you will get the equation for d square x by dt square is equal to minus d by lx. So this is the solution. So that is how we see what is simple harmonic motion, and we also try to understand the terminology used in simple harmonic motion, the amplitude, and what is angular frequency, and the time period, for example, because we know for the circular motion the time period is t is equal to 2 pi w. So from this we get the time period, and frequency, there's a number of cycles per second or the number of rotations per second is nothing but f is equal to 1 over t. So these are the basics of simple harmonic motion which we have tried to understand. So this is part 1, and please look at the next video on part 2, in which I try to explain solutions for typical problems involving simple harmonic motion.